Okay, hi everyone. So this is the minimal polynomial of an operator, section 5b. So first let's look at these two questions up here. Prove every operator has an eigenvalue, and then give a counterexample and restate the correct theorem. So let T be an operator. So what was it? It was every operator from V to V, a linear map is an operator from V to V, on a complex vector space has an eigenvalue. Okay, so how do we prove this? So the idea is choose a non-zero vector, okay? Then if you just start writing down the list, v, t squared v, because v is an operator, we can do it twice, we can do it 3 times, so we can actually do a whole polynomial in v. And once we get up to the dim v many times, this is dim v vectors, and then this is one more, so we have dim v plus 1. That's too many vectors. They cannot be independent. Are dependent. So that means there's some linear combination of them. A naught v plus a1 tv plus a2 t squared v plus all the way up to whatever it is equals 0. But that basically means that we have a polynomial. So factor out v from everything. A naught plus a1t plus a2t squared plus dot 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 times v equals 0. But this is a polynomial where we replace the variable like x squared, x to the third with the operator t. So there exists a polynomial with p of t equal to 0 for that v. Okay, so then how does that help us? Because we have a theorem, the fundamental theorem of algebra says that p of x has a 0. In other words, some lambda in C. Now this is the fundamental theorem of algebra over the complex numbers, meaning the 0 might be complex, okay? That's why we need a complex vector space. P of x has a 0, so some lambda in C exists with p of lambda equals 0. Okay, how does that help us? Well, that means that p is equal to x minus lambda times some other polynomial q of x. So p of x is equal to x minus lambda q of x. Because if you have a root, you can always factor this out. How do we prove that? Remember, we had the division algorithm that every p of x is equal to, well, we can divide by x minus lambda. Nobody can stop us from taking this polynomial and dividing it by x minus lambda, and then getting a quotient, and then a remainder. And what we're going to see is that the remainder has to be 0 if lambda is a 0 of the polynomial, because if you plug in p of lambda, we said p of lambda is 0, right? But if you plug in p of lambda over here, you get lambda minus lambda times q of lambda, which q of lambda might not be 0, but this is 0. 0 times q of lambda is definitely 0. And then we have r of lambda plus r of lambda plus r of lambda. Okay, so r of lambda has to be 0 is what we've proved. And if that's true, then by induction on the degree of the polynomial, remember in the division algorithm, when we divide a polynomial by something else, the remainder has one less degree at least, or it has strictly less degree. So then this has r of lambda equals 0. So then we can divide r of x, the polynomial r of x, by x minus lambda, and get some other q tilde of x plus, and just repeat the process. Now we get even smaller degree, and you can't just keep doing this forever. So then we could show that, you know, this would have to be 0, and by induction on the degree, we get that what do we get? We get that this remainder, this original remainder, was actually 0 the whole time, which means that x minus lambda divides p if lambda is a root of the polynomial, okay? So that was a proof actually from chapter 4, but just so you know how this works, p of x has a 0, so that implies p of x equals x minus lambda times some other polynomial q of x plus no remainder, okay? So that means p of t is t minus lambda times the identity q of t, okay? And we know that p of t v is 0, so if we apply v to this, we get 0, or we apply this to v, we get 0, because p of t v is 0. Okay, but that means, what does that mean? So remember, v is non-zero. We just chose some non-zero vector. So either q of tv is 0, or it's not 0 as a vector. If it's not the 0 vector, if q of tv is not the 0 vector, then q of tv is an eigenvector with eigenvalue lambda, because t times q of tv minus lambda times q of tv is 0, but that means t of q of t v equals lambda times q of t v. And that just says that q of tv is an eigenvector provided it's not 0. Now, if it is 0, same thing. We're going to do induction on the degree. So if it is 0, then q of t v is 0. And q of t has strictly smaller degree. It has degree 1 less than p, because we took p and we divided it by a linear x minus lambda. That means q has degree 1. If p had degree 4, q has degree 3. So now we have that a smaller degree polynomial is 0 on this vector, but q of x is a polynomial again. So q of x has some other root. Maybe it's lambda tilde, or maybe we can call it mu, okay? Where mu is in the complex numbers, the fundamental theorem of algebra, and we just repeat the result. So what your book does is it says, okay, when we take this original polynomial that we know exists, definitely some polynomial exists such that p of tv is 0. So let's just choose it of minimal possible degree, okay? And then that means that this can't be 0 because q has smaller degree. So then this is a non-zero vector, and hence it's an eigenvector with eigenvalue lambda. Okay, and so your book just says, there exists a polynomial of smallest degree such that p of tv is 0. And that's the idea. So that's why every complex vector space has an eigenvalue. Sorry, every operator has an eigenvalue. A complex vector space doesn't have eigenvalues. Operators have eigenvalues. Okay, but the key here was that you had to be finite dimensional, because that is what gave us at least some polynomial p of t v equals 0. Okay, so that's why it has to be finite dimensional. Give a counterexample. So it just multiplication by x. So if you have v be the infinite dimensional space of all polynomials, then let t from v to v take a polynomial and multiply it by x. So f of x would go to x times f of x. That's a linear map. Multiplication by x is a linear map on this infinite dimensional space, and it has no eigenvalue it has no eigenvalue because it has no eigenvector. If you had some polynomial that when you multiply it by x, it's just equal to lambda times the original polynomial, that is a contradiction, because x times f of x would have degree 1 more than f. But if you just scale f by some like 5 or 17 or 1 plus I, the degree doesn't go up. Okay. So what's the minimal polynomial of an operator? The minimal polynomial is, first of all, it's a polynomial. Let's say p of x, such that, and now here are the keys. What do we need it to do? P of t v is 0 for all vectors v. So that's different. Last proof, we just chose some non-zero vector and then blah, 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 and got a polynomial. Here, we want it to be 0 on every possible vector for all vectors v and v. Another way to say that is that p of t as an operator is the 0 operator. So it's the 0 operator. Just everything, you feed it something and it gives you 0. Okay, what else? Such that 1 p of t v is equal to 0 for all vectors little v. What else? Oh yeah, p has minimal, the smallest degree of all the polynomials for which this is true. So if you collect all the polynomials that satisfy this, that are 0 on every vector in the vector space, choose one that has the smallest possible degree. Okay? P has minimal degree of all possible polynomials satisfying 1. Satisfying the first condition. And then what else? The highest degree term of p should be 1. Just rescale p. If there was a 2x to the 5th and it had degree 5, then divide everything by 2. So highest degree coefficient of that polynomial should be 1. And why do we do that? Just to say that the minimal polynomial is unique. Okay? Because if p of tv is equal to 0, then 5 times the polynomial p of x would also give another p of tv equals 0 for all vectors v. So we just say, okay, let's make it unique by making its coefficient 1. The word for that is monic. It's a monic polynomial. Okay. So that's the idea. Now let's show that, that it exists. Prove existence and uniqueness. Okay. So how do we prove existence? So let v be non-zero. Now this isn't going to work because we need it to be 0 on everything, but just do what we did last time. So choose v non-zero and do exactly what we did last time. Create these. Obviously they're dependent because you can't have more independent vectors than the dimension. So you get some polynomial p of t, which on that special vector that we happen to choose is 0. Okay, that's fine. And that we're not done yet. Okay, so then now we have p of t v equals 0 for one vector v. Now we need one for all. So why does it exist? Well, the idea is look at the range of p of t. So p of t is an operator, right? T is an operator. So then we create a new operator, p of t, which does t a bunch of times and then linearly combines the results in some way according to the coefficients of the polynomial. And that's an operator, so it has a null space. You can look at the null space of p of t, and you can look at the range of p of t. And it turns out both of these are invariant under t again. Okay, so they're subspaces that we know, and they're invariant under t. And by the fundamental theorem of linear maps, we know that the dimension of the vector space is equal to the dimension of this plus the dimension of this. So what we're going to do is use induction on dimension. We want to show that a minimal polynomial for an operator t exists on a finite dimensional vector space. Okay, so let's just check if the dimension of v is 1, then t of v has to be lambda v. Like there's no other way to get a linear map on a one-dimensional space other than just scaling it. Okay? And so clearly t minus, this is an eigenvector already. So we're good, there is we're not looking for eigenvector. We need a minimal polynomial. So what's the minimal polynomial of t from v to v, where v is one-dimensional? Let p of x be defined to be x minus lambda, where t scales things by lambda. That's all t can do on a one-dimensional space if it's going to be a linear map. Okay? So t is definitely equal to lambda times v for some lambda. Then write down this polynomial. That's minimal. So it exists for dimension 1. now what we're going to do is, by induction, assume it exists. What's it? The minimal polynomial for t exists for every operator, exists on all vector spaces of dimension strictly smaller than the dimension of our vector space dim v. Okay. And so then what we're going to do is we're going to show that on the range has strictly smaller dimension. Well, how do we know that? Well, look at p of t times v is equal to 0, and v is non-zero. We chose some special v that was not 0. We found a polynomial that sends it to 0. That means this dimension is greater or equal to 1. Okay, but that means that this dimension is strictly less than the dimension of the whole space. Okay, so then look at t restricted to the range of p of t. Well, that's an operator on a smaller dimension. Thus, there exists a minimal polynomial there. There is a min poly for t restrict to the range of p of t. Call it q of x, okay? So what does it mean to be a min poly? It means that if you apply t, I'm not going to keep writing the restrictions too much, to any vector in the range, in the space, which now is this range that has smaller dimension than our original space, is 0 for all w in the range. Okay, so then here's the nice thing now. Now we can apply p of t. No, wait, what do we do? Yeah, okay, so then p, q, how about f? Now the polynomial f of x, let it be q of x times p of x. Okay? And that's actually going to be a polynomial that does what we want. So consider now for any little vector u in our whole space, for any vector in our whole space, f of t on u is equal to, well, q of t, p of t applied to u, this is now in the range of p of t. By definition of the range is all the things that you can, the range of p of t is all the things of the form p of t times a vector. Okay? Well then, q of t is the min polynomial on range p of t, and so this is 0. And that's true for all u and u. Thus, f of x is a poly. It definitely exists, is a polynomial with f of t, u equals 0 for all little u in the big vector space capital V. Okay, so now there exists some polynomial that's 0 on every vector. Thus, there is one of smallest degree. And then divide by coefficient of highest degree to make it monic. There we go. Now we've got a minimal polynomial for t on the whole vector space V. And the key was looking at the invariant subspace range of p of t and showing that it had strictly smaller dimension, so we could do induction on the dimension of our vector space. Okay, how about uniqueness? Uniqueness is easy. Let p and q be two min polys. Then they have the same dimension, which would be the minimal possible same degree, the minimal possible degree for t, v to v. And they both have the highest degree coefficient is a 1. So then consider f of x defined to be p of x minus q of x. We're going to show it's 0. Well, why is it 0? Because f of x applied to any vector in the space is just, f of t, now let's let's plug in the operator t, is just p of tv minus q of tv. But p and q are both minimal polynomials. That means this is 0 and this is 0. In other words, f of x and f of t satisfy the conditions to be a min poly too, except because they're subtracted off and these two had the same highest degree coefficient, the highest degree term vanished. And so f of x has smaller degree than p and q, which is a contradiction. That can't happen. And so clearly the only way that can happen is if f of x is actually the 0 polynomial. But if f of x is the 0 polynomial, that just means that p and q were the same. So if you had two minimal polynomials, they have to be equal. Because if you make their subtraction, you get another minimal polynomial of smaller degree. Do you know what I mean? How the highest degree terms, like let's imagine we had x to the 5th minus, what number is that? 3x4 plus blah, blah, blah. That was p. Let's say that was p. And then q was x to the 5th. You know, q can't be 2x to the 5th. P and q have to be monic. And so then, I don't know, maybe it's 4x to the 4 minus 7x to the 3rd. And this was a 13x to the... Who knows? This can't happen. Because if you subtract them, you get a polynomial of lower degree. It would be degree 4 plus degree 3. And this would be the minimal it would satisfy the same requirements as a minimal polynomial, but have smaller degree. So then p and q weren't minimal in the first place. Okay. All right. The next few questions here I'm going to do in a separate video about how to actually compute the minimal polynomial. Surprise, surprise, you just solve a linear system of equations for the unknown coefficients of that polynomial. Okay, but we'll do that later. Let's focus on the proof right here next. Okay, prove that lambda is a 0 of the minimal polynomial if and only if it's an eigenvalue of t. Okay, so this now justifies maybe more clearly why we're interested in this. The eigenvalues of t are going to be the most important things to understand t. They're going to be the energies in quantum mechanics, etc., etc., etc. Very important. They'll tell us how to solve differential equations. They'll tell us the stability of equilibria in differential equations. We care about the eigenvalues of t. And guess what? The eigenvalues of t are exactly the zeros of the minimal polynomial. Exactly the zeros. So let's see that. So say p is the min poly of some operator t from v to v. And say p of lambda is 0. So lambda is, maybe it's a complex number, or maybe it's a real number. Do we care? I don't know. Let's see. I think it'll work. It won't matter the field, so it could be real or complex here. How do we show? Oh, if we have a root, we can factor. We can factor p of x. We can divide it by x minus lambda, get a quotient, and then the remainder is 0, as we talked about earlier. So whenever you have a root of a polynomial, you can factor out a linear factor that corresponds to that root. Okay, how does that help us? Oh, because, well, hold on, how does that help us? So we have a 0 of the minimal polynomial. What are we trying to show? That it's an eigenvalue of the operator. Ah, I see. Because remember what a minimal polynomial does? If you feed in any vector here, you get 0. Okay, but now using the factorization, p of t is just t minus lambda times the identity times after q of t, v is 0. And this is true for all vectors v because that's part of the definition of being a minimal polynomial is you're 0 on every vector. Okay, so now if this is non-zero, we're done because then it's an eigenvalue. Then lambda is an eigenvalue. Okay. I hope you know that now. So being in the null space of t minus lambda times the identity, so if some vector w is in the null space of this, that just means that tw minus lambda w is 0, which means that tw is lambda w. And so w is an eigenvector of eigenvalue lambda, provided that w is not the zero vector, okay? So we just have to show that this thing is not the zero vector, and then we're done. Then this is an eigenvector showing that lambda is an eigenvalue. We assumed lambda was just a zero of the min poly, and we're going to get that it's an eigenvalue with eigenvector q of tv. Now, why does this have to be, if this was zero, then q of x would be a minimal polynomial of smaller degree than p. Now, here's where it's important for all v and v. So, in other words, if this was zero for, if q of t was zero, if this was zero for all v and v, then p was not minimal. Because q would satisfy the conditions of being a min poly, but q has one less degree than p. The degree of q is 3, then this has degree 4, and that's bigger. So that means that there is some vector in our space, let's call it little w in v, with q of t, w, not the zero vector, but then q of t, w, is an eigenvector, with eigenval lambda. Okay, so we assumed that lambda was a zero of the min poly, and we've shown that every zero is an eigenvalue. Okay, what about the other way? Let lambda be eigenvalue of t. Okay, then there is some non-zero vector with tv equals lambda v. That's what it means to be an eigenvalue. We have to show now that lambda is a zero of the polynomial. How do we show that lambda is a zero of the polynomial? Well, it's actually a little tricky. But the key is that if tv equals lambda v, what's t squared v? Well, it's t on tv by definition, but t on lambda v. But then t is linear, so the lambda pulls out, and we get tv again. But tv is lambda v. So we get lambda times lambda v, which is lambda squared v. And very similarly, t to the third v is lambda to the third v. And t to the kv is lambda to the kv. And now, what is p of t on v? If v is an eigenvector, then remember p of t is just some polynomial, let's say it a to the k, t to the k, applied to v. But t to the kv is lambda to the kv. So this ends up being a sum coefficient a sub k lambda to the kv. But what is this? Factor out the v again, and we get p of lambda times v. Okay? And so that is 0. Why is that 0? Because p is a minimal polynomial. So it's 0 for all vectors, including this eigenvector, whose eigenvalue is lambda. But then each of the t's just pulls out more lambdas, and you just end up getting a scalar out here. V is just, when p of tv is 0, well, p of tv is a scalar times v. And remember, v is not 0 because v is an eigenvector. And eigenvectors aren't 0. So how could a scalar times a non-zero vector be 0? It means that the scalar was 0 in the first place. This number, the polynomial, and we replaced every x with lambda. Actually, we didn't do that. We let t apply, but then it had the same effect. That means lambda is a 0. Okay, so we did our two proofs. Zeros of the minimal polynomial are exactly the eigenvalues of the operator. Okay, let's see if there's more to do. Let's do these two, or these three, and then we'll leave these ones for another video. So the minimal polynomial, prove that if some other polynomial satisfies this, then f equals qp for some other. Okay, so let p be the minimal polynomial of an operator, and then if there's some other polynomial f that satisfies the same condition, then it has to just be a multiple of p. you know, it might have higher degree if it's not the minimal polynomial, but it satisfies this condition that it's 0 on all vectors, then we need to prove that it just looks like this. So certainly we can always divide the polynomial f by the polynomial p, and we'd get some quotient plus some remainder. Okay. And now the key is we have to apply what we know about f and what we know about p. We're saying f is some polynomial with this being 0 on all vectors. Well, p is a minimal polynomial, so it does the same thing, except it has smallest degree. So let's apply f of t to v. That means we're going to do p of t, q of t, v plus r of t, v. Now, q of t, v is some vector, so p of t on it is 0. So this whole term is 0. F of t on the vector is 0 by assumption. We're saying f is some satisfies that same. So we get 0 equals 0 plus r of t 0. R of t v is 0. And this works for all vectors because that's what we said f does. F hits any vector we want and gives 0. But this says that r of t also satisfies the property of the minimal polynomial condition, except by the division algorithm, r has strictly smaller degree than p, which is a contradiction. Then that would mean p was not minimal after all. The only way out of this is if r is actually the 0 polynomial. Then it doesn't contradict minimality of p, but it does mean that p divides f. There is no remainder. Okay, good. So then an easy corollary is that the minimal polynomial of t restricted to u divides the minimal polynomial of t. So what does that mean? We've got some big space v and we've got some operator on it. Then we take some subspace, some smaller, possibly smaller subspace, and we restrict t to that subspace, where now u is an invariant subspace, I believe it should say. It should say, yeah, u is an invariant subspace. Otherwise, we don't get another operator. And the claim is here, the minimal polynomial of this operator on a smaller space divides this minimal polynomial up here. Okay, so if this had the minimal polynomial q of x and this had p of x, then p of x is just q of x times some other polynomial. So that we'd say q divides p, right? So the minimal polynomial, the restriction divides this one. Now, why is that true? Well, what is the definition of this? If this is minimal, then q of t u is 0 for all u and u. Okay. But p of x satisfies that p of t v equals 0 for all v and v. But that includes all the u's. So p satisfies the same condition as q. But we just finished proving that if a polynomial satisfies that same condition, that it's 0 on all vectors, then it's got to be a multiple of the minimal polynomial. So that means that this one, which satisfies the same condition, it gives 0 on all the vectors in u, must be a multiple of the minimal polynomial of u. And that's exactly what we were trying to prove. Okay, so that one's done. Now, what about this one? Prove t is invertible if and only if the minimal polynomial has constant term 0. So remember, what is the minimal polynomial? The definition is that for all vectors, when we feed it to p of t, p is the minimal polynomial if this is 0 for all the vectors. Okay. What are we trying to prove? That its constant term is 0. So let's imagine what it might look like. It might look like a0 plus a1x plus a2x squared plus a3x to the third, okay? And if its constant term is 0, that means it actually looks like a1x plus a0 is 0, so it actually looks like this, okay? In particular, every term has at least one x. Okay, so this is what we want to show. And if that's the case, then p of t is just going to be a1t plus a2t squared plus a3t to the third, etc. Okay, and we know it's 0 when you plug in any vector. Okay, so what are we trying to prove? t is invertible if and only if the minimal polynomial has constant term 0. So if the minimal polynomial has constant term 0, then guess what's a root? How could we get 0 out of this polynomial? Well, p of 0 is 0. Right? Every term has an x, so if you replace x with 0, you get a 0. But what does that mean? Remember, if p of lambda is 0, then we can factor p as x minus lambda times some q of x. But here we're going to have p of 0 is 0. So then p of x is actually equal to x minus 0 times q of x. Okay. So why does that mean that the operator is not invertible? Oh, because we proved that zeros of the min poly correspond to eigenvalues of, so this is if and only if. Okay, what is happening? Let me do a good job. So, 0, okay. P of x has constant term 0 if and only if p of 0 equals 0. But every 0 of the minimal, in other words, 0 is a 0 of p of x. Okay, but every 0 of the minimal polynomial is an eigenvalue. So 0 is an eigenvalue of t. That we proved earlier. What does that mean? That means t minus lambda I v equals 0 for some non-zero vector. Right? That means tv equals lambda v. But here our lambda is 0. Minus 0 times the identity. Okay? In other words, tv equals 0 for some non-zero vector. Right? But that means that the null space of t is not only 0. But remember, for a operator from the same dimension input space to the same dimension output space, that means t is not invertible. Okay, and everything here was if and only if from previous theorems. T is not invertible if and only if blah, blah, blah. P of x has constant term 0. So that's the end of the proof. Okay. It was really crucially used previous theorems from the book, including from chapter 3, that T is not invertible exactly when the null space is non-zero. You know, it fails. Another way to say the null space is non-zero is it fails to be injective. That was from chapter 3. Because our linear map went from V to V, then the input and output space have the same dimension. And that was key. All right, I'll stop for now, and then I'll do some other videos on this last part about real vector spaces, which is tricky, and then also some computations on how to actually find the minimal polynomial now that we know all the proofs about it.